Welcome to General Chemistry. I'm Jim Burnham. Today we're talking about chemical reactions. This is Chapter 8. On May 6, 1937, the airship Hindenburg was about to land in Lakehurst, New Jersey after crossing the Atlantic. These were giant dirigibles filled with gas, and they were experimental aircraft, but they had been very, very safe up to this time. Suddenly, to the horror of everyone on the ground, the airship erupted into a fireball as nearly 1 million cubic feet of hydrogen burst into flames. Here is, it was actually recorded.
Nearing the fatal end of her first Atlantic trip of the season, the Hindenburg approaches the mooring mast at Lakehurst. 21 of these sky voyages the world's biggest dirigible has made. So safely, so surely that the experimental service has become a matter of routine. Scarcely 100 feet above ground, the giant airship with her framework encasing 7 million cubic feet of inflammable gas is being carefully maneuvered towards her hangar, when suddenly...
So it's filled with hydrogen gas, and a single spark was enough to set it off. Watch down here.
The inexplicable, appalling tragedy is a matter of seconds. It seems almost incredible that anyone should escape. Yet 2/3 of those on board survive what is, next to the R-101 disaster, the worst in the history of aviation.
So, the chemical reaction that caused the Hindenburg disaster can be described rather simply as hydrogen combines explosively with oxygen to produce water. Here is the chemical formula for that, the chemical description. Again, 2 hydrogens, 1 oxygen, to produce 2 waters. And all you need is a flame or a source of ignition. We are surrounded every day by chemical reactions. Cooking things, eating and digesting things, photosynthesis, our car batteries, our cell phones, rust. All of these chemical reactions involve changing substances. So these are not just physical changes that we talked about in earlier chapters. This is a chemical change that involves a change of substance. So the first section of Chapter 8 is going to be how we describe chemical change. So we need to be able to describe chemical reactions in writing. Just like in the previous chapter, Chapter 6, we needed to describe chemical formula in writing. Remember, there were millions of chemical formulas, and we had several rules that we used. Remember, all the way back in Chapter 2, our shorthand method for describing chemical reactions. Reactants yield products. Or, this was the symbol means. It means we could also say gives or produces. But so the reactants produce or give or yield the products. Remember Dalton's atomic theory about chemical reactions? As reactants are converted to products, the bonds holding the atoms together are broken. The atoms themselves are not broken, but the bonds holding them together are broken and new bonds are formed. Again, Dalton believed that all chemical reactions were the result of the rearrangement of atoms, not the destruction or the creation of new atoms. So, in model form, 2 hydrogens plus 1 oxygen yield 2 waters. But the atoms themselves are neither created nor destroyed. Look, over here we start with 4 hydrogen atoms, 2 oxygen atoms, and this is our reactants. And in our products, what do we have? 1, 2, 3, 4 hydrogen atoms and 2 oxygen atoms. The same number of atoms we have in the reactants as we have in the products. So again, we're not creating, we're not destroying, we're simply shifting them around, we're rearranging them. And that's why each side of the equation has to have the same number and kinds of atoms. Atoms aren't created or destroyed, merely rearranged. This is this explains the law of the conservation of mass. Atoms in the products are the same atoms that we had in the reactants. They're just arranged differently. And we're going to see it's very important to keep track of them and to write balanced chemical equations. So how do we write chemical equations? Well, we can describe chemical reactions in different ways. Here is a classic example of rust. This is what happens when my children, for example, leave my tools out in the rain. So a word equation to describe this would be iron plus oxygen yields iron 3 oxide. The chemical equation to this would be, we would use the symbols, Fe plus O2 yields Fe2O3, iron 3 oxide, which is what we learned back in chapter 6. That's how you write iron 3 oxide, which is an ionic compound. This is known as a skeleton equation. A skeleton equation, it gives us a chemical reaction that does not show the relative amounts of reactants and products. But a skeleton equation is an important first step to later getting the full and correct chemical equation. So we can also add physical state to our, so remember back here we were just saying, look, iron plus oxygen gives us this. Now the reason we call this a skeleton equation is that we've got 2 irons here in our result and 3 oxygen here in our result, and we only have 1 iron accounted for here and 2 here. So you can see that it's unbalanced. A skeleton equation will be unbalanced. It is just giving you the nuts and the bolts, the basics of the equation, without necessarily balancing the atoms. We can also add physical state to our skeleton equation. So we write iron in the solid state, so we use parentheses and we use S for solid, plus O2, which is in the gaseous state, yields iron 2 oxide, or was it iron 3? I've already forgotten. Iron 3 oxide, which is in a solid state. So these parentheses, they tell us the state, the physical state of these various particles. In many chemical reactions, a catalyst is something that speeds up the reaction without itself being used up. So often we'll use a catalyst to help speed up the rate of reaction. So for example, if we take hydrogen peroxide decomposes slowly into water and oxygen. It can take months for this to happen, and this is why, if you buy your hydrogen peroxide and then months and months later you try to use it, it seems to have gone flat. It has. It's been decomposed into water and oxygen. But with a catalyst such as manganese 4 oxide, the reaction can be done in just minutes. So catalysts never produce more product, but they produce the same amount more quickly. So it allows the reaction to go from maybe a slow reaction to a relatively fast reaction. And in a chemical reaction, when we're writing this in formula way, we would add the catalyst right over our yield arrow. And so we would say manganese 4 oxide. We would indicate this over the arrow that it is part of this reaction as a catalyst, but it doesn't. It's not part of the reaction proper. It's not really a part of the reactants. It's not really a part of the products. It's just something that helps this reaction get there faster. So the equation must follow the law of the conservation of mass. We have to balance both sides of the equation, just like an algebraic equation. Suppose you were building a bike. And your word equation would be something like this. So you've got a frame, you've got wheel, you've got a handlebar, you've got pedal, and you have a bicycle. And you could turn that into a formula by using some basic symbols. So let's use F for frame, and W for wheel, and H for handlebar, and P for pedal. And so our skeleton equation would be frame plus wheel plus handlebar plus pedal equals frame, 2 wheels, handlebar, 2 pedals. Now, as you can see, this isn't balanced, right? We have 2 wheels over here in the product and 2 pedals over here in the product, but we only accounted for 1 here in the reactants. So it's right qualitatively, but it's not quantitatively right. It doesn't show the quantity of parts needed. And so when we balance equations, we have to make sure that each side of the equation has the same number and kind of elements, of atoms, the same number of atoms of each element. So our balanced equation, back to our bicycle, would be frame plus 2 wheels plus a handlebar plus 2 pedals equals our finished product, frame, 2 wheels, handlebar, 2 pedals. It's balanced because it gives the correct quantity of each reactant and product. So the numbers in front of the symbols, we just call those coefficients, just like algebra. If there is no coefficient, it's assumed to be 1. So this would be assumed to be a 1. This is obviously a 2, a 1, a 2, and so on. And this whole thing would be a coefficient of 1. So why do we have to balance? Because of the law of conservation of mass. As we said, matter is neither created nor destroyed. So you have to start and end with the same amount. So if you have 30 kilograms of log and you have a kilogram of fire, you're going to end up, that's 31 kilograms, then your products have to equal 31 kilograms. Oh, 28 kilograms of ash, 3 kilograms of smoke. Your end is the same as your beginning. So a balanced equation means that each side of the equation has the same number of atoms of each element. All right, here are the rules for balancing chemical equations. And we're going to go through the more complicated rules and then a more simplified form. But feel free to go back to this to get the details. So the first thing we're going to do is determine the correct formulas for all reactants and products using what we know about elements and compounds. So we're going to use what we know, for example, from Chapter 6 about how to make balanced ionic compounds, balanced molecular compounds. So we're going to write the formulas for the reactants on the left and the products on the right with a yield sign in between. And if we have 2 or more products or reactants, then we're going to separate them with plus signs. So this will give us the skeleton equation. Now we count the number of atoms of each element in both sides, the reactant side and the product side. And for simplicity, if you have a polyatomic ion appearing unchanged on both sides, that is counted as a single unit. So treat your polyatomic ions as a unit. Don't break them up into individual atoms. That will be very, very challenging. Balance the elements one at a time using coefficients. Begin with elements that only appear once on each side of the equation. Very important, do not change the subscripts. If you're working and you have an O2 and you say, well, I need one more oxygen, what if I just turn that into an O3? No, can't do that. Don't change subscripts, but you can change coefficients. Once you've done that, once you've balanced the elements using coefficients, then you're going to check each atom or polyatomic ion to make sure that the equation is balanced. And then finally, you're going to make sure all your coefficients are in the lowest possible ratio that balances. If you have, for example, a 2, a 4, a 2 on this side, well, those can all be divided by 2, and so you would get a 1, a 2, and a 2. Anyway, so you want to make sure that you're in the lowest possible ratio. Now, I'm going to simplify these into just 2. Write the correct skeleton equation, and then choose coefficients if necessary to balance all the atoms. So here would be an example. Here's the word equation. Methane combines with oxygen to yield carbon dioxide and water. Here would be the balanced chemical equation. Oh, we didn't write our skeleton, but that's what. So before we would have methane CH4 plus O2 yields CO2 plus H2O, and then we would realize that we need to use a coefficient in front of the oxygen and in front of the water to make sure that our oxygens balance out with our hydrogens. And this is just an atomic model of what's going on. Here's another example. Word equation. Magnesium combines with oxygen to yield magnesium oxide. All right, our skeleton equation would be magnesium plus O2. And our balanced chemical equation would be recognizing that because each magnesium only has 1 oxygen and we have 2 oxygens to deal with, we've got to double our product, which means we have to also double our beginning magnesium. And so with a coefficient of 2 in front of the magnesium and a 2 in front of the magnesium oxide, we can balance our equation. This takes us to our second section, types of chemical reactions. There are basically 5 main types of chemical reactions, and we will go through them each individually. Just like there are millions of known chemicals, you would expect there to be millions of different chemical reactions, and there are. But just like we learned in Chapter 6 to name those millions of chemicals by following a system or a pattern of naming, so too we can recognize patterns of chemical behavior that let us characterize and predict the products in many, many reactions. And so we can basically characterize most chemical reactions, not all, but most, in 5 different broad groups. And so here are the 5 different types of chemical reactions. One is called combination, also known as synthesis, where you are combining one thing out of 2 or more beginning things. Then you have decomposition, which is the opposite of combination. Here you're building something up, here you're tearing something down. We also have single replacement, we'll talk about that, double replacement, and combustion. We've seen some examples of combustion. The Hindenburg was a classic, terrifying example of combustion. So here are the 5: combination, decomposition, single replacement, double replacement, and combustion. Remember, combination is also sometimes known as synthesis. So just get used to seeing one or other of these words and be able to switch between them if necessary. Reaction number 1, combination or synthesis. This is where 2 or more substances combine to form a single product. So we've already seen this reaction. Magnesium plus oxygen yields magnesium oxide. So again, here's your skeletal chemical equation. Here is the balanced chemical equation. And you have 2 products on the reactants and then 1 product on the product side. So 2 reactants and 1 result. Oh, and here is that reaction, just a video of this reaction. We would do it in class, except that it burns so brightly. Magnesium burning in oxygen is so bright that it will damage your eyes. You have to look at it behind cobalt glass. So here is a safe way to view this reaction. Here is the magnesium, right there, a stripped ribbon of magnesium being ignited by a Bunsen burner. You see it burns with incredibly intense. Now they put it into a jar filled with oxygen. So now this thing is just blind your eyes bright. And it's going to, that combustion is going to continue until it runs out of the oxygen. And in the process, it's turning that magnesium into magnesium oxide. So most common combination reactions are either 2 elements or 2 compounds. So we just saw one with magnesium, that's an element, plus oxygen, that's an element, produces or yields magnesium oxide. That's an example of this first kind where we are synthesizing something from 2 elements. But we can also do it with 2 compounds. And the product is always a compound, right? Because we're combining what are our starting stuff. Whether we start with elements or compounds, our result, our product is always a compound. Now, what determines if that compound is ionic or molecular? Yep, we're not going to get away from these words. Ionic and molecular, they're going to follow us around. Well, it depends on the type of reactants. If you are reacting a metal, as we did in that last one, magnesium is a metal, and a non-metal, oxygen, your product is going to be ionic. This is going to be an ionic compound, just as you would expect. If you react 2 nonmetals, then your product is going to be a molecular compound. So this is just like our ionic compounds and molecular compounds in chapter 6. Metal and nonmetal, ionic, 2 nonmetals, molecular. Potassium, for example, reacts with chlorine to form an ionic compound. Write the correct formula for the product by considering the charges of the anions and the cations. Remember, this is all back to chapter 6. So our skeleton equation is potassium combines with chlorine to yield potassium chloride. Now this is our skeleton equation. It's not balanced necessarily. And as we can see, as we examine it, it's not balanced. We have 2 chlorine atoms here, but only 1 in our product. So to balance this, we're going to have to double this, and then that's going to force us to double this. So now we have a coefficient here and here, and now we have a balanced ionic equation. Notice that we'll get to this. We'll get to the charges in a second. Okay, 2 nonmetals. If you react 2 nonmetals together, you will often get more than 1 product, and we'll see why in just a second. So, for example, if you take sulfur, a nonmetal, and react it with oxygen, a nonmetal, you would predict that you would get sulfur dioxide, which you do. But you can also combine two sulfur atoms with 3 oxygen, and you can get SO3. So you can get multiple forms of the oxide here. So here's sulfur dioxide, and then it's also sulfur trioxide. So depending on the amount of oxygen being sucked in to this reaction, you can get multiple products, and this is common. Sometimes chemistry is messy, and you have to account for what we call byproducts or multiple products. You don't always get what you're aiming for in a reaction. This also happens if you react a transition metal and a non-metal. You'll often get more than one product. So here is a reaction with iron reacting with sulfur to produce iron 2 sulfide. But you can also get, if you react 2 irons with 3 S's, you can get iron 3 sulfide. And again, both of these reactions are possible, and so you get a mix of a percentage of each of these reactions in your total reaction. Our second kind of reaction, remember our first one is combination or synthesis, where we're building up a compound out of 2 starting elements. Well, this is the opposite. This is decomposition. Instead of building something up, we're going to break it apart. In a decomposition reaction, a single compound is broken down into 2 or more products. And that can be any combination of elements and compounds that it is broken down into. So here is, remember we did electrolysis of water? That's an example of a decomposition. We take water molecules and we break them up into, in this case, it's elemental parts. 2 hydrogen, 1 oxygen molecule. This is calcium carbonate, which is a solid. If you heat it up to about 1200 degrees Celsius, it breaks down into calcium oxide and carbon dioxide. And this is a solid and this is a gas. Extremely rapid decomposition can produce heat and gas. And when that happens, you get an explosion. I'll say it again, extremely rapid decomposition that produces heat and gas equals an explosion. That's what's happening when something like dynamite goes off, or a bomb goes off. You have extremely rapid decomposition, producing gas and heat, and it tears things apart. Here is the formula for the decomposition of TNT, which is trinitrotoluene. It's a tough word to say, so I'd say that 3 times fast. So 2 moles of this breaks down into 3 moles of nitrogen gas, plus 7 moles of carbon dioxide gas, plus 5 moles of water in the gaseous form, so steam, plus 7 moles of carbon in the elemental form. But notice this, 2 moles of TNT produces 3 plus 7 plus 5. That's 15 moles of hot expanding gas. And it's that hot expanding gas that tears things apart. Our third reaction we want to consider is a single replacement reaction. What does this mean? Well, it means where one element replaces a second element in a compound. So diagrammatically, it looks like this. A and B show up to the party, but C is over here looking pretty handsome, and so B says, you know what? I'm going to leave A and go with C. So C, if you look at this, replaces A. So right here, A is bonded to B. C is the new kid in the room. And what the end result is that A is left by itself, and now C is hanging out with B. And so, yeah, C has replaced A in this reaction. And first C was alone, now A is alone. This happens when potassium reacts with water, and we've seen a video of that, of this very vigorous reaction where potassium reacts with water. And in this, what's happening is potassium, so here's potassium, and here's water. And if you look carefully, this potassium, there's two H's here at the beginning. You have an H, you have two H's and an O. Over here you have an H and an O, and that other H has been kicked off, has been replaced. The potassium has come in here and replaced a hydrogen, and that hydrogen is now just out of the picture, and so it recombines as a diatomic molecule. But so potassium takes hydrogen's place in this water molecule and replaces one hydrogen. When this happens, hydrogen is released as a flammable gas, and so this is a way to produce hydrogen gas. So here is a meme that I rewrote. So here's the metal you came with, and then here's the metal you're going to leave with, because that's an upgrade, I guess. This metal is hotter and finer than this metal. So whether one metal will replace another metal from a compound can be determined by the relative reactivities of the two metals. Remember, different metals have different reactivities, and we can rank them, and this is called a activity series. So this is known as the activity series of various metals. And what you'll see here is we use hydrogen as kind of a reference point. So hydrogen, we're just going to say this is 0. And metals that are less reactive than hydrogen will be below hydrogen. So we basically we rank them from the most reactive metals in decreasing reactivity. So the most reactive here, these are the hottest girls. These are all 10s and maybe some 9s and some 8s. And if you're the anion, you're going to trade up if you can. You're going to trade your partner. So let's say you come in with zinc, but then you see magnesium there. You're going to trade zinc for magnesium, because magnesium is a hotter property. It's more reactive, and it will displace zinc if zinc shows up. If zinc dares to show up to the club. So basically, you want to be potassium, and even you don't see it here, but lithium is even more reactive than potassium. So you really want to be lithium if you want to always get the girls, the hottest girls. So this is This is an activity series. Everything. So any metal will replace any metal below it. So sodium will replace magnesium. Magnesium will replace zinc. Zinc will replace iron. But it doesn't go in the reverse. Iron will never replace zinc, and zinc will never replace sodium. The lower will never displace the higher, only the higher the lower. So a reactive metal will replace any metal listed below it in the activity series. So here we have magnesium and zinc. So we look at this, we see magnesium and zinc. Magnesium is more reactive. So we can predict that magnesium is going to come and just take zinc's place, kick zinc out with this nitrate. And that's exactly what happens. The magnesium, which comes in as a solid, in aqueous zinc nitrate, it displaces the zinc, and you end up with magnesium nitrate and zinc as a solid. So yeah, bye-bye zinc, hello magnesium. Again, and we can see why, because magnesium is more reactive than zinc, and thus any metal above it will replace any metal below it. How about magnesium and silver? Okay, magnesium, silver, all the way down here. Yeah, very, very unreactive and highly reactive. So of course magnesium is going to replace silver. So, and that's what we see. Magnesium is going to come in here, kick silver out of the way here, and give us a yield of magnesium nitrate, and the silvers are going to aggregate over here and become a solid. So silver nitrate walks in, but magnesium nitrate walks out, because magnesium is more reactive. Magnesium is a hotter property, a hotter girl, if you will, and that's who you're going to hang out with at the end. Okay, what about this? Do we have a reaction if we had magnesium and lithium? I don't have it here, but no, lithium is even more reactive than potassium, and magnesium will never replace anything above it. So you won't get a reaction from this, because lithium is already the hotter property. If magnesium walked in with nitrate, lithium would replace it. But here, lithium is already the hottest thing in the room, and nothing is going to displace lithium and the nitrate. So we get no reaction here. So we only get a single replacement reaction if we have a more reactive metal. In nonmetals, replacement is usually limited to the halogens. Remember, the halogens are the group 7A, right next to the noble gases. And it's usually limited to just these four. And each of these is a decrease in reactivity from the one above it. So fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. And so fluorine will replace a chloride. Chloride will replace a bromine or an iodine, but not the reverse. Bromine will never replace a chloride. It just won't happen. Only the more reactive will replace the less reactive. So this is a decreasing reactivity of these halogens. Okay, the fourth reaction we want to consider is called a double displacement. So if you can have one element replacing another in a compound, what if you did, like square dancing, a double partner replacement? What's that called? A do-si-do? No, that's not it. I don't remember my square dancing. But there, you can switch partners. You can both switch partners, and that's what's going to happen in this double displacement. So it's an exchange of positive ions, cations, between two reacting compounds. Oh, notice, yeah, that's another way to describe the single reactant is that what's going to change is the cations. It's going to be an exchange of the positive ions, usually a metal. So you're exchanging cations. Here is the cation you came in with, and here is the hotter cation that you're leaving with. Okay. Where are we here? Double displacement. Double displacement. So A and C are both cations. They are both, for example, metal. And what you're going to see is that they're going to switch places. They're going to switch partners. So A came in with B, but A is going to leave with D. And C came in with D, but C is going to leave with B. So your cations, your positive ions, are going to replace each other in the dance with the negative ions, the anions. That's a double displacement reaction. It usually takes place between two ionic compounds in aqueous, that is, in water, in a water solution. And it often produces a precipitate. A precipitate is something insoluble that will drop out of solution, and you will actually see it cloud up and then just form a solid out of this aqueous solution. So here's an example. You have this yellow precipitate dropping out of solution, and it will pool up here on the bottom. For a double replacement reaction to occur, one of the following is usually true. One product is only slightly soluble and precipitates from the solution. So that's for this to happen, you usually have a product that is soluble, only slightly soluble, and will easily precipitate from the solution. So, for example, you have sodium sulfide plus cadmium nitrate, both in aqueous solution, and it yields cadmium sulfide, which is a yellow precipitate. I think that's the reaction we see here. That might be a lead precipitate too. Anyway, and then so sodium shows up with sulfur, but goes home with nitrate, and cadmium showed up with nitrate, but went home with sulfur. The second thing that could be true is that one product is a gas and bubbles out of the mixture. So the first thing that can happen is you get a precipitation that forms. The second thing that happens is you can get gas bubbling out of the mixture. So here's a double displacement reaction, right? Sodium shows up with chlorine, and hydrogen shows up with a sulfate. And but sodium goes home with the sulfate, and the what happened here? It doesn't make sense. I'm gonna have to reword. I've got stuff in my reaction here that doesn't make sense from my anyway. We will fix that. The third thing that can happen is that one product is a molecular compound, such as water. So you can, a precipitate can form. That's the first thing that can happen. The second thing, a gas can form and bubble out of the water, or it can produce water, more water. And so here we have calcium, who shows up with this oxide. I'm going to say hydroxide. And here is hydrogen showing up with chlorine. But what's going to happen is that the calcium is going to go home with the chlorine, and the hydroxy group is going to go home with this extra hydrogen and become water. So you have this crisscross of the cations, a double displacement of the cations. The fifth reaction type that we're going to look at is combustion. We've already seen some examples of combustion. A combustion reaction is where an element or compound reacts with oxygen, often producing energy as heat and light. So our Hindenburg burning is also an example of a combustion reaction. Hydrogen, the element, reacting with oxygen, producing energy and massive heat and massive light. Combustion reactions commonly involve hydrocarbons, which are compounds made out of hydrogen and carbon, just like the name suggests, hydrocarbons. This is the subject of organic chemistry, but these things produce energy. They produce energy when you burn them, like propane or butane. They produce energy when your body burns them, like sugar, glucose. So combustion happens. Combustion powers a lot of things. It powers us. Our energy comes from a combustion reaction. Complete combustion of hydrocarbons will yield carbon dioxide and water, which is why, going back to biology, right? After our body digests sugars, hydrocarbons, we breathe out oxygen and we also exhale vaporous water. So that is the result of complete combustion gives you carbon dioxide and water. But incomplete combustion, which is usually caused by a lack of oxygen or insufficient oxygen, what will happen is that it will create carbon monoxide and elemental carbon. So that's why we have to be careful when we combust things, especially in enclosed spaces. If there's not enough oxygen, you can create this poisonous carbon monoxide, which is an odorless, invisible, but deadly gas. And anyway, so yeah, that's what causes it, a lack of complete combustion, incomplete combustion. The reaction between some elements and oxygen is also an example of a combustion. This should be an example of a combination reaction. So we've already seen this. We've already seen magnesium combining with oxygen to produce magnesium oxide. We saw this as an example of a combination reaction, and it is. But it's also an example of a combustion reaction because it's reacting with oxygen. So you can classify some reactions in more than one way, and this is an example of that. Both a combustion and a combination or synthesis reaction. Same here. So those reactions were previously identified as combination reactions, which is correct, but also combustion reactions because they're reacting with oxygen. How do we predict the products of a chemical reaction? Well, you can look at what you have. Look at what you have what are you starting with? If you're starting with two elements and you end up with one compound, chances are that's synthesis. If you start with one compound and you get multiple compounds in the reaction, in the result, that's probably decomposition. If you start with one compound and one element, that's a good chance that it is a single replacement reaction or possibly a synthesis. So this could go in this category or this category. If you have two compounds, again, it could be synthesis, two compounds combining, or a double replacement. If you have a hydrocarbon and oxygen, it's combustion. It's combustion. And oftentimes, anytime you have a reaction with oxygen, it will be a type of combustion. So we can look at this diagrammatically as well. So here, A plus B yields AB. So if you have two substances in the reactants and one compound in the product, good chances it's a synthesis reaction, combination reaction. You're combining AB to be AB. Combustion. Here you're combining A with oxygen to produce an oxide. And this happens, you can do this with a metal and oxygen, a non-metal and oxygen, a compound and oxygen, and you get these results. Decomposition is when you start with a compound and you break it up. You start with AB and you break it up into A separate from B. Single replacement, B shows up with X, but A replaces B and A goes home with X, and B goes home alone. Double replacement, A and B switch places. A goes home with Y, B goes home with X, AY, BX. The third section is reactions in aqueous solution. Aqueous solution just means water. Before we start with net ionic equations, which is what we're going to talk about in aqueous solution, first we need to recognize that our world is a water world, a water-based world. 70% of our Earth's surface is covered by water. And depending if you're female or male, up to 65% of your body weight is comprised of water. Your eyes are 95% water, your heart 75% water, your muscles 75%, lungs, blood obviously 94% water. So we are water-based creatures in a water-based world. And so it shouldn't surprise us that many important chemical reactions take place in water, that is, in aqueous solution. And you've already seen the symbol for that, AQ, in parentheses. So consider the double replacement reaction, silver nitrate plus sodium chloride yielding silver chloride plus sodium nitrate. So what happened? Silver showed up with nitrate, but went home with chloride. Sodium showed up with chloride and went home with nitrate. So they crisscrossed, they switched places. Now, in this reaction, we often this is the right reaction, but it is a little bit simplified, because what we're recognizing is, as you probably remember from chapter 6, when you have an ionic compound, many ionic compounds dissolve in water. In fact, that's what aqueous means. It means that this has been dissolved into a solution in water. So you don't really have silver bound up with nitrate here anymore. It's basically separated. And sodium and chloride, they separate in water. So what you really have, what we really should do is write this ionic compound with the ions separated after they've dissolved. And so it would look like this. The complete ionic equation would be silver ion plus nitrate ion. Remember they were together before they were dissolved in water. And the sodium and the chloride were together, but now they're dissolved in water. So the sodium ion is separate from the chloride ion. And then it yields silver chloride, which will precipitate out as a solid. And the sodium and the nitrate, they're just going to stay in the water. They may line up, but they are not going to come out of solution because they are going to stay dissolved. And so when we look at this, you can see that some parts of this reaction things are changing. This silver ion gets bound up with this chloride ion. But notice what happens here. This nitrate is just hanging out in aqueous solution in the product side, in the reactant side. It's also hanging out over here in the product side. It's nothing changed. Likewise, sodium is hanging out as an ion in the reactant side, and then likewise sodium is hanging out here in the product side. So we call those spectator ions. They're just hanging around watching the action. They're just wallflowers watching other people dance. These guys are dancing. They are having a reaction, but the nitrate is standing around on both sides. The sodium is standing around on both sides. So we can eliminate those spectator ions. We just cross them out. And that gives us our net ionic equation. So remember, we go from a a complete balanced chemical equation, we rewrite it as the complete ionic equation by breaking all those ionic compounds into their separate ions and then seeing what's going to react out. We cross out the spectator ions, and that leaves us with our net ionic equation, which is now this. Silver ion, aqueous solution, plus chloride ion in aqueous solution yields silver chloride in a solid form. It's going to precipitate. That leaves only the particles that actually take place in the reaction. When we remove the spectator ions, we are left with the actor ions, the ones that are actively involved in the equation. These are the ones actually changing. So be aware that a problem might ask you for all those things. What is the complete ionic equation, and then what is the net ionic equation? And the difference there is you're going to cross out spectator ions, things that are the same on both sides and don't change from one half of the equation to the other. A spectator ion, those are like people that go on a double date and then they watch while their partners get together and dance. It's a bummer. Wah, wah. In writing net ionic equations, you must also balance the ionic charges. This is important. So, for example, in this case, we have silver with a +1 charge and chloride with a -1 charge, and so that's going to balance out. This ionic compound that results from this is going to be electrically neutral. It's going to be balanced out by the positive and negative charges of the ions. But consider this reaction. So you have lead as a solid, and here you have this aqueous solution of silver nitrate, and you already know this is going to break up into its ionic, its ions, and this is going to produce silver in the solid form and lead in the nitrate form, again in aqueous solution. Now notice that this is a single replacement reaction, right? Lead is going to replace this less reactive metal and go home with the nitrate and kick the silver to the curb by itself. And we can see that this nitrate is going to, it's an aqueous solution here, it's an aqueous solution here. That nitrate, when we write the complete ionic equation, is going to be a spectator ion. So it's going to end up being crossed out. So it's going to give us a net reaction of this, of lead plus the silver ion yields a silver solid plus lead, which is 2+, has a double positive charge. This, as you can see, is unbalanced. Why? Because you have here you have two positive charges on the reaction side, but only one positive charge that you began with. And remember, everything has to balance. If you start with 2 positive charges here, you have to end up with 2 positive charges here. So to balance that out, we've got to add a coefficient to silver. We've got to say, well, if we're going to end up with 2 positive charges here, we've got to have 2 positive charges on my silver to counterbalance, to make sure that the positive charges are the same on both sides. So we're going to add a coefficient here and a coefficient here to make sure that our charges are balanced. Here I have 2 positive charges counterbalancing the 2 positive charges on this side. Whatever's on this side has to also be on this side. So, of the 5 types of reactions identified in this chapter, both single replacement and double replacement reactions can usually be rewritten as net ionic equations. So do be aware of that. These reactions, they usually involve ionic compounds. They don't, not exclusively, but they often do. And those ionic compounds are almost always dissolved in water. They're almost always in aqueous solution, so they're going to dissolve into their ionic constituents. And the spectator ions can be crossed out, and you get the net ionic equations. This takes us to another section known as predicting the formation of a precipitate. We saw that sometimes you will get these solid reactions out of these single and double replacements. And that is indicated by something that is insoluble. It comes out of solution and forms what's known as a precipitate. So mixing solutions of two ionic compounds can sometimes, not always, but can sometimes result in the formation of an insoluble salt called a precipitate. And so you're going to have to become familiar with these solubility rules. And while it looks daunting, it's really fairly simple. You start with this one. All nitrates are soluble. So anything with a nitrate is going to be dissolved. It's going to stay dissolved. So even if it's part of the double reaction, even if it gets a new partner, it and its new partner are going to stay in solution. All ammonium, that's this polyatomic, or alkali compounds. Remember, the alkali are the group 1A metals. All of those compounds are soluble. So lithium with anything, lithium with any polyatomic, sodium with any polyatomic, they're going to be soluble. So these two will get you through a lot of trouble. In fact, I think in the AP chemistry exam, you just have to know these two solubility rules. They give you the others when you need them. But it's helpful to know a few more than just the first two, although the first two are the most important. All carbonates and phosphates and hydroxides. So you remember I told you we're going to have our polyatomics are going to come back over and over again. So we have to know our polyatomics. But of our polyatomics, the carbonates, phosphates, and hydroxides are insoluble except with these guys, because these guys make everything soluble. So normally carbonates, phosphates, and hydroxides are insoluble unless it's these alkali guys. Any alkali guy at the party makes everything soluble. All chlorides, bromides, and iodides are soluble except, there's a few big exceptions, silver, lead, or mercury, and there's a couple others. Finally, all sulfates are soluble except with some of the group 2A metals, and then also lead. So barium. So anyway, so just remember, all sulfates are soluble except with these few exceptions. So again, most important rules: all nitrates are soluble, all ammoniums are soluble, all alkali compounds are soluble, and that even overrides when things that are generally insoluble. Okay, summary questions. Why must chemical reactions be balanced? Why? Okay, because in a chemical reaction, atoms are neither created nor destroyed. So all the atoms present on the reactant side must also be present and accounted for on the product side. What are the five main types of chemical reactions? Well, we've seen combination, decomposition, single replacement, double replacement, and combustion. And four of those are represented here. Here is combination or synthesis. Here's decomposition. Here is single replacement, where C replaces B, and double replacement, where A and C both get different partners. This is kind of an interesting way to, if you're a visual person or a verbal person, maybe this might help. Think about this way: synthesis, note plus book comes together to combine for notebook. Decomposition is the opposite. Bookworm breaks down into book plus worm. In an exchange reaction, a single replacement, you have notebook plus worm. Well, the worm is going to come in here and kick out, replace note. And you're going to have bookworm, and note is going to be by itself. So note shows up with book, but book leaves with worm. What is the activity series and how is it used? The activity series of metals is a list of metals in order of decreasing reactivity. So it lists them from the most reactive to the least reactive, and we can use it to predict if a single displacement reaction will occur. So here is the activity series of the metals, from lithium down to gold. This is the most reactive. This is the least reactive. Metals can replace any metal that is below it. Metals above hydrogen can also replace hydrogen in acid. So all of these will replace hydrogen in acid. And metals from sodium and above, these four will replace hydrogen even when hydrogen is in water. So they'll pull the hydrogen right out of the water. The end. Thank you for your time and attention.